So let's learn more about ionic compounds. Minerals are ionic compounds. That's what we call them when we find them in the Earth's crust. The Earth's crust is just full of ionic compounds. They are also present in the foods that we eat. They're present in our bodies. Ionic compounds are all over the place. Ionic compounds are very stable, generally, because that ionic bond, that charge between oppositely charged ions, is very strong, and so that the solid tends to be a very stable substance. Here's two examples of ionic compounds that you might consume. Light salt. Probably know, maybe a father or grandfather needs to watch his sodium intake, right? Because he eats too much salt and his ankles swell up and his blood pressure goes through the roof, and that's all bad. So one way to flavor your food and not get as much sodium is to use light salt. Well, what makes it light? It's not fewer calories. Salt doesn't have any calories. It's got less sodium. And it gets less sodium because it's a mixture of sodium chloride and potassium chloride. And so you don't get as much sodium when you sprinkle an equivalent amount of that on your food. It is a mixture of two ionic compounds. That's all it is. And we eat it. Tums. Antacid, you might need that if you have heartburn or something. This particular antacid, the active ingredient is calcium carbonate. This is another form of calcium carbonate, the mineral called calcite. And it's called calcite because here these ions are arranged in a particular way. And we'll talk more about that in one of the last chapters this semester. Here's another example of an ionic compound. So ionic compounds can be rocks that you would not want to eat, but they can also be substances that are good for you. So when we write formulas for ionic compounds, we always write the symbol for the metal first and the non-metal second. And in order to put those two things together into a formula for the compound, we need to know what the charges on the ions are, because it's the charges that dictate, well, do I need one sodium and one chloride, or do I need two chlorides? The charges have to balance. So when we're writing formulas, the first step is to write the symbol for each of these ions, the metal cation with its charge, followed by the non-metal ion with its charge. You're going to have one plus and one minus. Now, I have some analogies, and none of them are meant to be politically incorrect, so please don't be offended. These are things that happen in what I like to call Mrs. K's chemistry land. It's like my Disneyland in my head, where atoms are alive and have personalities and all sorts of strange things happen. So one of the ways I think about this is I think about metals in general as being masculine, and non-metals then will be non-masculine or feminine. So I think of the metals as being masculine, the guys are metals, and the non-metals are girls. So when you write out a formal wedding invitation, one of my boys is getting married in about a month or so, you write these formal invitations. How do you address things? Mr. and Mrs. Do you write Mrs. and Mr.? No. Why not? Because that's not how we do it, right? It's just tradition, right? It has no meaning of who's more important. It's just a convention, right? So when we write these ionic compound formulas, it's Mr. and Mrs. It's the masculine, the metal first, and then the non-metal. Always. Just because. That's how everybody does it, okay? So we need the metal and the non-metal ions with their charges, and then we're going to look at the charges, and that's what's going to tell us how many of each of those we need to put together. So we adjust the subscripts to get a balanced overall charge, and then we have to double check that we're doing it okay. So ionic compounds always have positive and negative ions. The first element, usually a metal. This is the one exception that I expect you to remember. that ammonium ion. Ammonium is nitrogen and hydrogen. They're two nonmetals, but together they make a positive ion. This one was on your list of things to memorize. That's the one polyatomic cation we'll see. In this class, everything else, the cation is a metal. The sums of the charges have to add up to 0. So you add up all the positive charges, and that must be equal to the charges on the negative ions. And then we're looking at the smallest whole number ratio of ions. So let's practice. Write the formula for the ionic compound that forms between potassium and sulfur. So, what's the symbol, the element symbol for potassium? It's K. Don't write with the highlighter. What's the charge on a potassium ion? It's +1, so we write just plus. How do we know it's +1? It's in group 1. We learned about the predictable ions in chapter 2. Group 1, metals form +1 ions. Group 2, +2 ions. Group 3, +3 ions. And then with the nonmetals, group number -8, or seems more intuitive to me, just count back from the noble gases. So sulfur is S, right? You look on the periodic table, and if you start on the far right side and count backwards, it has what charge? -2. Because argon would be 0, chlorine's -1, sulfur's -2. So I'm going to write that as 2 minus. We don't want to write -2 because that looks like a variable to the -2 power. So it's always the number first and then the sign. So that's the first step. Cation with its charge, anion with its charge. Now we look at these charges and we say, well, how many of each of these do we need so that when we put them together, their charges will add up to 0? We need 2 potassiums and 1 sulfur. So we'll write K2S. Now many of you just see that and you're like, oh yeah, I see how that works. Other people don't, and that's okay. So there's different ways to think about it. We can just draw pictures, which can be very helpful in the beginning. So what I'm going to do is down here below, I'm going to add up the charges. It's not really anything to add, but over here, I've got a +1 charge, and over here I have a -2 charge, because this one is a -2, 2 minus, and this is +1. These numbers are not the same. I need +1 and -1, +2 and -2, +3 and -3, something like that. Well, I can't change the charges. All I can do is add more ions. So I don't have enough positive charge, so if I draw another potassium ion, now the total positive charge is +2. See that? And so I got +2 and -2. I've got the right ratio. Then I just count up how many of these do I have? K2. I got 1 of these. S. I don't write the 1 because chemists are lazy. Any questions? Have you heard of the crisscross method? So students tend to like the crisscross method, and it works like 90% of the time. Occasionally it'll get you into trouble, but I'll show it to you anyway. So here I've got K plus and S2 minus. The crisscross method, most important first step that will save you from getting into trouble most of the time. Look at the charges. Are they the same? No. If they are the same, you don't need to do anything, just shove them together and go on. They're not the same, so we could crisscross. So I'm going to take the number on that one, and that's going to be the subscript for the other one. And I'm going to take the number, and that's going to be the subscript for this one. Leave the charges up there. So I've got K is going to get a 2 from here, and the sulfur is going to get a blank because there's a blank up there. And that's the formula. Let's do aluminum and nitrogen. What's the symbol for aluminum? Al. And what charge does an aluminum ion have? Yeah, +3. So we would write that as 3+. And that's because aluminum is a main group metal in group 3. So it's got a +3 charge. And then nitrogen is N. And what charge does the nitrogen ion have? 3-, counting backwards on the periodic table. So I look at these and +3 - 3. Do I need to do anything to them? No. Just push them together. A, L, N. It is important to make your capital letters and your lowercase letters correctly. I know some of you like to write in all caps, and you've got big caps and little caps, and that's great everywhere except element symbols. So A, L, I don't care how small that L is, that's a capital L, right? So that's not okay. And sometimes students, because you were taught to put all these little tails on your letters in elementary school, sometimes you put a tail there on that L. Try not to do that, okay? Because that looks a lot like a kind of sloppy capital L. And so that's one of the reasons why I like to make my lowercase l's a script L. There you can have your little tail at the end. It's very clear this is a lowercase L. And for that nitrogen, sometimes students give me that. Like, that's a capital. No, that's just an overgrown lowercase n. So this is an example of what not to do. It's just not correct. It's got to be a capital N. Anywhere else in your writing, I don't care as long as I can read it. Elements, symbols, you got to do them correctly. Okay, that's how we write formulas. How do we name them? Some compounds have common names. They're just, like nicknames. Everybody uses them. Water is an example. Water is not the systematic name for H2O, but it's the one that everyone uses. Some compounds have multiple common names, and so that can get confusing. So there is a system for naming all compounds so that each compound has one best correct name. We're going to learn how to use the system. The first step is identifying what kind of a compound you have, because different kinds of compounds have different patterns for naming. People in different countries and cultures have different patterns for naming their children. My ancestors came from Sweden. They don't do this anymore, but in the old days, if your father's name was John and you were a guy, your last name would be Johnson because you were the son of John. And if you were a girl, your last name would be John's daughter because you were John's daughter. It's pronounced the same, but it was D-O-T-T-E-R, make it look more Scandinavian. So you can imagine things could be a little confusing because, here's Peter Johnson and his son is Lars Peterson, right? And then, anyway, I forgot what I said, so I can't continue that analogy anymore. But you need to know, here in the United States, typically a child, male or female, gets the father's last name, regardless of whether the mother took the last name or not. And some of those things are changing a little bit. There are exceptions, but that's a pattern, right? There are other countries where they do different things. So we need to identify what country or what culture these compounds come from so that we can use the correct system to name them. So we've learned how to identify ionic compounds. The first element is a metal. That's the key. There's only one exception to that you need to remember. If it starts with NH4, it's an ionic compound. But here we have some examples. Sodium bromide, that's a metal, metal. Those are all ionic compounds. Your book divides the ionic compounds into two groups, and I'm going to talk about it because, I don't want to confuse people, but I think this is a little bit silly. It comes down to there's two kinds of metals. There's metals that only form one kind of ion, and those would be the ones we've talked about, group 1A, 2A, and 3A. Sodium only forms a +1 ion, never anything else. There are other metals, though, like iron. Iron can form a +2 or a +3. And so when we name it, we need to specify which of those ions are we talking about. So we use a Roman numeral to indicate the charge. It's a little bit, again, like naming people. And you have John Smith, and you have John Smith Jr., and you have John Smith III and John Smith IV, right? You've all got the same name, but they're different people. So you need that suffix at the end of the name to specify which of those you're talking about. And that's what happens with this second type of metals. They can form different charges. So let's cover the ones that are always the same first. Group 1A, Group 2A, Group 3A. You're like, why aren't the rest of these? Well, gallium, indium, and I think that's thallium. We don't run into those very much. Really, it's just aluminum over there. There's three others. Scandium, another one which we don't run into very much. Zinc and silver. Zinc and silver are common. And I'm going to repeat this so often that you'll be chanting it in your sleep. So groups 1A, 2A, 3A, zinc and silver. Groups 1A, 2A, 3A, zinc and silver. Those are the metals that always form the same kind of ion. We don't need to specify junior or senior because there isn't one. This guy is unique. Nobody else has that name that you know of, at least. Okay? We're going to leave scandium out of that because it's just not going to come up. So the names for these ions are just the element name. The sodium ion, we don't do anything to its name. It's just sodium. Aluminum ion is just aluminum ion. Then there's the other metals. So that's one category, group 1A, 2A, 3A, zinc and silver. And then there's all the other metals. Okay? All the other metals, as far as we're concerned, can form more than one kind of cation. And which one it is depends on the compound, and you don't necessarily know. And so we need to specify what it is. We don't know if we're talking to John Smith III or John Smith IV. We need him to identify himself. So we use Roman numerals, just like, the kings of England. Henry VIII, Henry VII, got Roman numerals behind their name. So here are some of the metals that we run across a lot that have multiple charges. So chromium, sometimes it's +2, sometimes it's +3. So when it has a +2 charge, we call it chromium 2. When it has a +3 charge, we call it chromium 3. That's pretty straightforward. Let's look at lead. Lead's down here. We've got Pb2+ and Pb4+. So that's lead 2. This is lead 4. What about lead 3? Well, lead doesn't do that. Do you need to remember that? No, because it's just not going to come up. You won't see it in a formula. You won't see it in a name. So we don't need to remember which kinds of ions they form. We just need to be able to recognize them and name them. This is an older system of naming these ions that we're not going to use. I just want you to be aware of it because it is still used in some situations, right? So like iron can be +2 or +3. They used to call this ferric and ferrous ion. And the us and the ick here just were relative. The us was the lower charge and the ick was the higher charge. But it didn't tell you exactly what the charge was. And the reason it's ferric is because it's from the Latin name for iron, which is ferrum, which is where the symbol Fe came from. And so these are older names. I remember watching toothpaste commercials as a kid, and they kept talking about stannous fluoride. Oh, this is better for you. It's got stannous fluoride in it. Well, stannous is tin 2. Saying that there's tin 2 fluoride in your toothpaste, people are like, I don't want to put tin in my mouth. Yuck. So they called it stannous fluoride because then people don't know what it is. Brief lesson in Roman numerals. The first few are pretty simple. We've got 1 is 1 capital I. 2 is 2 capital I's. 3 is 3 capital I's. Then things get a little more complicated because we couldn't just keep going. That would just like tally marks. I'm going to skip to 5. 5 is a capital V. I don't know why, it just is. 5 happens to have a V in it, but so for 4, 4 is 1 less than 5. It's the number right before 5. So the Roman numeral for 4 is 1 before 5. And 6 is 1 after. So 6 is VI. Yeah, we probably won't get any higher than that. And then when you get up to 10, 10 is an X, and then I forget all the rest of them. There's L's and D's and M's and C's, and it's a little bit complicated. So you can be thankful that we don't have to do math with Roman numerals. That would be really unfortunate. Another word about Roman numerals, mastering chemistry can tell the difference between a lowercase l and a capital I when you type the name in as an answer. It's going to look the same on the screen. But if you put 2 lowercase l's in as the Roman numeral, it's going to tell you your answer's wrong. It has to be 2 capital I's. When you write it, 2 straight lines inside parentheses, I'm good with that. I can't tell what you meant them to be. But mastering chemistry can tell. Any questions? So this is just a restatement of my kind of mantra about metals. Groups 1A, 2A, 3A, zinc, and silver. No Roman numeral. Because my oldest son, James Kawagoa, do we go around referring to him as James Kawagoa the First? No. Because there is no other James Kawagoa in the world. Right? It's a really odd last name, even in Japan. So you don't just toss Roman numerals on the end of your name unless you need them, right? Because it just makes everything long. So these guys, groups 1A, 2A, 3A, zinc, and silver, don't need a Roman numeral, and so we're going to leave it off, okay? Everybody else needs a Roman numeral. Now, there's this triangle here. So here's aluminum is +3, zinc is +2, silver is +1. The way I remember that, aluminum is in group 3A, and then I'm going downstairs. 3, 2, 1. +3, +2, +1. These guys over here also fall into a pattern that gallium and indium are +3 and cadmium is +2. Those are unusual metals, and we don't run into them very often. So I don't feel like cluttering up my brain with them. Okay, so that was the cations. What about the anions? There are monoatomic anions and polyatomic anions. Mono means 1. So these guys have 1 atom as an ion. Polyatomic have many. So monatomic ions, we take the element name and we just change the ending. And this follows into my thinking of masculine and feminine for metals and nonmetals, because you could think of, well, when the metal and the nonmetal come together to form a compound, it's like they're getting married, right? And we list the guy first and then the girl, and typically the woman will change her last name, right? Not as common as it used to be, but it's still very common. So here's fluorine. She's getting married. And so she changes She only has the one name, so she can't change her last name, but she changes the end of her name. So fluorine becomes fluoride. Chlorine, chloride. The pattern breaks down a little bit here because you also drop the YG. Oxygen, oxide. So for the metals, just their name, Roman numeral if needed. For the nonmetals, you take the element name and you just change the ending to "ide." Okay. Questions? So binary ionic compounds are composed of two different elements, a metal and a nonmetal. And so when we name them, we just name the metal first, and there's a little space, and then we name the nonmetal. So if it's just a single atom, then you just change its element name ending to "ide," and there you've got it. So let's look at examples of that. So here's an ionic compound, KCl. To name this, we look at the elements that are in it. We've got K for potassium and Cl for chlorine. So the name for the potassium ion is just potassium because he's in group 1A, doesn't need a Roman numeral. Chlorine is the nonmetal, and so she changes the ending of her name to "ide." And so the name for this is potassium chloride. It's not potassium chlorine because that would sound like a list of elements, right? It's potassium chloride. Names of compounds are not proper nouns, they're not capitalized. If you look at CaO, we've got calcium and oxygen. So we have to figure out, well, calcium is the cation. Is it in groups 1A, 2A, 3A, zinc, or silver? Yeah, it's in group 2. Does not need a Roman numeral. We don't want to write more junk than we have to. So that's just calcium. And then oxygen is a monoatomic anion. We take oxygen, change the ending to "ide," oxide, calcium oxide. So let's name this compound, Ag3N. What are the two elements? Silver and nitrogen, right? So we got silver and nitrogen. You don't have to write down the element names, but I'm just doing that. Okay, so the first element is silver. So we write down silver, and then we ask ourselves, group 1A, 2A, 3A, zinc, or silver? Duh, it's silver, right? Or silver. Doesn't need a Roman numeral. Then I'm going to look at the next one, nitrogen, and I have to change the ending to "ide." So that's nitride. Now, if you wrote nitrogide, I would snicker to myself and cross out the extra letters. I wouldn't count it wrong. You'll become familiar with it after a while. Silver nitride. What about the 3? Don't need to do anything with the 3. We don't need to specify the 3 because if we just had the name silver nitride, we know what the charges are from the periodic table. Silver has a +1 charge. Nitrogen has a 3- charge. And we know that when we put those together, crisscross or adding things up, least common multiple, whatever your way of doing it is, you need 3 silvers to balance the charge on 1 nitrogen. So we're not going to say it's silver or trisilver nitride or anything like that, okay? Write the formula for rubidium sulfide. Well, this is like what we did before. You write the formulas for the 2 ions first with their charges. So rubidium is Rb. What's its charge? +1. Because it's in group 1, right? Sulfide, S, 2-, counting back on the periodic table. How do we put those together? Rb2s. Because when I have 2 of these, I'll have a total of +2 charge. one of these, -2 charge, when I put those together in that ratio, the thing is neutral. Okay? Any questions?